Hi, hello everyone. Today's topic is binary search tree. A binary search tree is a binary tree in which for every node all the elements in its left subtree are smaller than that node and all the elements in the right subtree are larger than that node. For example, consider this binary tree in which you take the root node 30, all the elements in the left side, that is 15, 10, and 20, are less than 30, and all the elements in the right side 50, 40, and 60 are greater than that node. And you take this node 15, all the elements left side are less than that 15, all the elements in the right side are greater than 15. Here also the same, that is this side it is less than 50, this side it is greater than 60. So this is a binary search tree. So a binary search tree is a binary tree in which all the elements in the left side are less than that node and all the elements in the right side are larger than that node. There is no restriction that the binary search tree should be a complete binary tree or a full binary tree. This complete binary tree I have just taken for an example. Another property of a binary search tree is that all the elements in a binary search tree should be unique. There should not be any duplicate elements in a binary search tree. A binary search tree is useful for searching an element. It's actually a combination of binary search and binary tree. In a binary tree, we inbuilt implement binary search. That's what we mean by a binary search tree. So it is useful for searching for an element in the binary search way. So the search happens like this. So we'll start off with the root node and assume that he is going to search for an element item. If the item is the data that is available in the root, for example, if you are searching for the element 30, then the data is directly available, then you can stop and it's a successful search. If the item you are going to search for is less than 30, then you can search in the left part of the binary search tree. If you are searching for an element in the right, greater than 30, then you can search for the element in the right part of the tree. So, and that is how we do the searching procedure in the case of binary search. So, if you are searching for an element less than 30, then you come to this smaller binary search tree and will proceed with the same binary search procedure. That is, we'll compare our item with this root node, and if you are searching for element less than 15, then we'll go here. Greater than 15, you will go to the right hand side. So if the item is less than the value of the root node, then proceed to the left child. If the item is greater than the value of the root node, then proceed to the right child. And the search process will be continued until you reach the dead end or until you get an element that is present, until you get a successful search. For example, if you are searching for the element 20, then you will come here 30. It is less than, 20 is less than 30. Then you come to the left side, 15. 15 is greater than, 15 is less than the item. Your item is larger, then you go to the right hand side. Here you found it. For example, if you are searching for an element 35, then you come here, then the item you are searching is greater, come here. The item you are searching is less, then you come here. The item you are searching is less, but there is no more elements. It's a dead end, so you can stop and say that the item is not present in your binary search tree. So once again, in a binary search tree, the search procedure is like this. If item is the data in the root node, then stop and a successful search. Otherwise, you split your data or split your tree into a left subtree and a right subtree. If the item is less than the root node, then you will search in the left subtree. If the item is greater than the root node, then you will search in the right subtree. Now let's talk about the properties of binary search tree. Initially, we have told that all the elements in a binary search tree should be unique, that is, there will not be any duplicate elements. In a binary search tree, if you do in order traversal, then you are going to get the elements in the sorted order. In order traversal is this: if first you go to left, then you print the data, then go to right. So you start from root node, for example, go to left, then what you get is there is no more elements here, then print the data. So the first element that will get printed is 10. Then you go up, then before going to the right, you print this. So after that 10, you will be printing 15. Then you go to right, so what you get is 20. So the sequence will be like this: 10, 15, 20, then 30, then 40, then 50, then 60. So in order traversal of a binary search tree is going to give you a sorted list of elements in the tree. The number of BSTs possible for n nodes is 2n Cn by n plus 1, which is this equation we have already seen while discussing binary tree, which is a property of binary tree. Searching in a binary search tree. Suppose you want to search for a key value 25. In this case, you will be starting from the root node. Take a temporary pointer to the t to that root node. Then you check t dot data and key is equal to 25. T dot data is greater than key, so you will come to left side here 20. Then you will be repeating the same number of steps again. Now t is 20, so t dot data is 20, so the t dot data is 20 and key is 25. So key is greater than t dot data, so you'll go to the right hand side and you will be doing the same procedure. So now key dot data and t dot data and key are the same, so you can say that your element is found and it is a successful search. The total time taken by the search operation will be order of h, the height of the tree. The height of the tree is log n and the maximum height is n, so the time taken is in between log n and n. Now let's discuss the binary search tree search algorithm, a recursive algorithm as well as iterative algorithm. This is the recursive algorithm. You take a pointer t, which is initially the root node. If t is equal to null, then return null. If key is equal to t pointer data, then return that value. That is, if the element is available at the root node itself. Otherwise, if key is less than t pointer data, then you do the same search procedure in the left child. If key is greater than t pointer data, and you do the recursive search procedure in the right child. That's it. In this case, if you are searching for an element less than 30, you will do the search procedure in the left part of the tree. If you are searching for an element which is greater than 30, you will do the search procedure in the right side. So that is these two recursive calls. If key is less than t pointer data, then recursive search t pointer left child comma key. So now t will be repointed to the left child, otherwise the right child. So that is the recursive algorithm. Now the iterative algorithm. Here also will be passing a pointer t while t not equal to null. So instead of an if statement here we need to use a iterative statement. So we'll be starting with a while loop, while t pointer not equal to null, while if t is pointing to null, that means that you are going to search in a tree which is null, so you return null. Otherwise, if key is equal to t pointer data, so this step was there in the previous case also. If key is equal to t pointer data, then return t. Otherwise, you rename or you increment your t to t pointer left child if key is less than data. If key is greater than data, you can increment t to, or you can change t to t pointer right child. Usually, we have seen that. Usually, we have seen that. Usually, we have seen that while converting a recursive procedure to an iterative procedure, then you may require a stack for converting, because recursive procedure is going to use a stack internally. So when converting a recursive procedure to an iterative procedure, you require a stack. But in this case we know that, sorry, we have seen that here there is no stack involved. Why? Because here the recursive procedure, in this recursive procedure we have been using tail recursion. So there are cases where you may not require a stack for converting or for changing your recursive procedure to iterative procedure, and that is very sure in the case of tail recursion. So this is an example of tail recursion, and while converting a tail recursive procedure to iterative procedure, there is no need of a stack uh, to be used. So this is the search procedure in case of a binary search tree, a recursive algorithm, and an iterative algorithm. The idea is very same. If key is equal to t pointer data, then return that. Otherwise, you search in the left part of the tree or the right part of the tree, just like binary search. Now let's look at inserting an element into a binary search tree, and then we can see how we can actually create a binary tree by just simply inserting element one by one. Suppose you have this binary search tree with you, then you would like to insert a key value 38. So before inserting an element onto a binary search tree, we need to search for that element in the binary search tree in the BST. So the first step is a search for this key value 38. So first we need to search for this key value. Why? Because the binary search tree has a property that all the elements in the BST are to be unique. If it is already present, then we should not insert it again. So there should not be any duplicate elements. So the first step is we need to search for the key value 38. While searching, we know the search procedure. Just we have seen the search procedure. So 38 is greater than 30. You go here. 38 is less than 40. You go to the left part. 38 is greater than 35. So if at all 38 was there, then the actual place where 38 was to be present was at this position 35. Now we are clear that 38 is not present, but 38 is greater than this node, so it can have two childs, a left child and a right child. So an element which is less than 35 only will go here. Now 38 is greater than 35, so it should go as a right child of 35. So we should insert 38 as a right child of 35 by creating a new node. So 38 will be inserted as a right child of 35. That's it. That's how we insert an element onto a binary search tree. So once again, we came with the value 38. 38 is greater than 30. Go here, which is less than 40. Go here, which is greater than 35. You create a new node and insert 38 here. That's it. That's how we create. That's how we insert an element onto a binary search tree. Now let's look at the procedure for inserting an element. So initially we need to search for the element for inserting. We are going to insert this value key. We take a pointer r and another pointer p. While t not equal to null, if t is equal to null, then you need to insert it as a root node. Otherwise, if t is not equal to null, then we write it as r equal to t. We take two pointers r and p. Let's see that. And then r equal to t, and we search here. If key is equal to t pointer data, then return t. Otherwise, you search in the left child. Otherwise, you search in the right child. So while searching, you will reach at some position, or at some position in the sense, in this case, while searching, you will reach at this position and you will say that this 38 is not present, and this element is a leaf node which is not having any left child and right child, so it is a dead end. At that position you will stop and you will come out of this while loop. Then into this node p we'll allocate that much amount of memory, how much memory is required for inserting this particular node. For inserting this node, we need to have a left child and a right child and a key value. So, in order to store these three, that is two pointers and one integer, that much amount of memory is allocated. Then p pointer data equal to key, that key is inserted. Then we say p pointer left child equal to null and right child equal to null. Left child and right child memory is allocated and we create it as null. Then if p pointer data is less than r pointer data, then we need to insert it as a left child. Otherwise, we need to insert it as a right child. In this case, we had came to this place and we created this node. Now we need to attach this pointer. Then we check whether 38 is less than 35 or 38 is greater than 35. 38 is if this key value is less than 35, they will insert it as a left child. If it is greater, then we will insert it as a right child. That's written here. If p pointer data is less than r pointer data, then insert it as a left child. Otherwise, you insert it as a right child. In the previous example, we have inserted with this statement r pointer child r child is equal to. So the first step is you search for that item. You will reach a position if the element is not present in the if the element is present, then you will return by this statement. If the element is not present, then we will reach a dead end, and at that place we will create a new node and we will attach it as a left child or right child. That's it. That's a very simple procedure for inserting an element. That's an iterative procedure. You can write the same in the way using a recursive procedure. You need to search for the element. Once again, here also you need to search for the element. The searching and inserting, everything will be done parallelly in the case of a recursive procedure. That is, here you create a pointer, sorry, a new node t, and to that t you allocate that key value and left child and right child as null. Then you just call this procedure again, recursive insert p pointer left child or right child. So if key is less than data, then it should be inserted as a left child. You call this procedure again and you come to this place. If at all the pointer p is null, then you attach that. Otherwise, this statement will not be executed. So once you reach a dead end, then this if statement will be executed. That's in the case of a recursive procedure. For example, let's see how we can create a binary search tree using the previous insert procedure. That is, let's say we have these keys 9, 15, 5, 20, 16, 8, 20, 12, 3, and 6. Let's say we have these keys. So the first element to be inserted is 9. Now elements are present. So the statement will be, the insert procedure will be easy. You create a new node and the elements left child and right child is kept as null. element is added as a root of the tree. That's it. The next key element is 15. So you come to the root node and check whether the element is greater than the root node or less than the root node. If it is less than the root node, then it should be inserted here. If it is greater than the root node, then it should be inserted as a right child. So 15 is greater than 9, so it will be inserted as a right child. Next key value is 5, that will be inserted as a left child of the root. Now this root node has two left and right child, so if the new element that is coming should be inserted in the next level, not in this level. So this is how it will be inserted. The element it will compare with 9 greater than 9, so it will compare with 15, it is greater than 15, so it will be inserted as a right child. So the entire set of elements, if you insert, after inserting all the elements, you will get a binary search tree like this. So what I'm trying to say is you can create a binary search tree by using the same insert procedure which we have seen previously by calling the insert procedure one by one. So we cannot control the height of the binary search tree. It is controlled by the sequence of the arrival of these keys. If the elements were coming in some other order other than the given order, then you might have got another binary search tree or a binary search tree with a different height. Okay, that's all in this video. Thank you.